process to wait on a semaphore. And similarly, as the I/O interrupt moves the process from wait for I/O into ready, the B operation then will move the process from wait on semaphore to ready. Okay? Is that understood? P is a software or hardware interrupt.
Software.
V is software or hardware? Software. Remember that we have I/O interrupt is hardware, and this one, what is the name of this one? Timer. It's hardware as well. Right? Okay. So look at this question. The kind of question I'm going to ask is, I can ask a question about semaphores on this state diagram without asking you to, probably asking you to draw this. But you can memorize that. But look, listen to this question. If a process is running, CPU, and execute a P operation, does it block? That is a P operation. Yes or no? Process trying to enter the critical section, apply the lock, but we call it P now. Apply the P operation. Does it block?
Like after the P operation?
No, when it applies the P operation. Remember, so we have several processes trying to enter a critical section. One of them, we could have many. One, but to enter the critical section, we have to apply lock and lock, but we call it now PMP. So the process applied the P operation. Does it block?
I would say yes.
Yes. Yes, if there is another process within the critical section. But if the critical section is free, why does it have to block? Because apply P and gets in. Because the operation P, let's assume that the value is 1, because we accept only 1 in the critical section. That is like the I/O operation. What we think is P block. So be careful. We decrement the value of the semaphore. Let's assume initially 1. Is the value of the semaphore less than 0? Initially 1, we apply the P operation. We decrement the value by 1. Is the value less than 0? No. So we don't get the then clause. We continue, enable interrupts, gets into the critical section. The process is running within the critical section, and there is a timer interrupt. Let's suppose that was process 1. Process 2 gets the CPU. Process 2 is running. Execute instruction and apply the P operation. Value semaphore is decremented by 1. Is the value less than 0? Is S less than 0?
Yes.
Yes. And when it's yes, add this process to the semaphore is blocked. Because we move it to the other state. So the process was running, the first one, getting to the critical section. There was a timer interrupt, it went back to ready. We assigned P2 here, P2 was running, applied the P operation. Sorry. Okay, P1 was running, execute the P operation, decrement the semaphore by 1. There was a timer interrupt when it was in the critical section, P1 is here. Now we send P2 for the running state. P2 is running and apply the P operation. Decrement the semaphore by 1. The value is negative, right? Negative 1. So it goes into wait on a second. So the answer there will be, when a process executes a P operation, does it block? Yes or no? And then you cannot say yes or no. You have to say it depends. If the value of the semaphore is less than 0, it blocks and goes into the semaphore queue. Otherwise, it continues running and enters the critical section. Can you see that? Initially, the value is 1. The first one decremented value gets 0, so it continues running. If there is a timer interrupt while P1 is running in the critical section, we're going to send P1 back to ready. Right? If the second process executes P, it increments again. Now the value is -1. And when it's -1, the process that is running moves into wait on semaphore. Similar to when we initiate an IO operation, it's conditional. Or the process continues running and enters the critical section, or if the critical section is busy because there is another process there, then the process that applies the P operation is blocked on a semaphore queue. Yes?
So the difference is it adds it to a queue as they come in. Is the benefit that it basically processes them as they come in? Or is it, so that
In what state are you talking? Are
So
you
you-
referring to?
compared to lock and unlock, I'm saying,
We're doing lock and unlock.
right, but it's, I'm saying like what's the difference, what is it adding, doing it this way?
Well, first, that we don't have busy waiting. Remember busy waiting that the process enters the critical section? When we implement that in hardware, we have this case of busy waiting. We lock, P is locked and B is unlocked. We lock, there was no one in the critical section, the process went in, was running, there was a timer interrupt, but the process is within the critical section, but it's sent to ready. Then we get process 2, try to enter the critical section, it's blocked, but it's not allowed to, but it's spent all the time checking. You remember the TIS operation, if TS is equal 1, go back, go. So wait all the CPU time given to the process to run, just testing if it will do anything. And that could happen for many processes, so wasting CPU time. Dijkstrat solved the problem in software, and we don't have busy waiting, because the process applied the P operation, if the critical section is free, gets in, continues running. If the process within the critical section, at that moment there's a timer interrupt, okay, you send it back to ready. Another process takes the CPU, apply the P operation, and then as there is another in the critical section, that process is blocked. But blocked in the sense that it's sent to the semaphore queue. And the CPU can be assigned to another one. And if all of them apply the P operation on the same semaphore, all of them will go into the semaphore queue. And the queue will be served first in, first out. Okay? So let's do this. You have P1, P2, and P3. Semaphore, initially 1. We assign the CPU to P2. P2 is running. And then, eventually, P2 applied a P operation. That means that the value of the semaphore goes down to 0. When the P operation asks if the value is less than 0, the process is blocked. Otherwise, it continues. So is the value less than 0? No. So the process P2 continues running and enters the critical section, which means it gets into the critical section. If there is a timer interrupt, P2 goes here, and let's say that this, the CPU is assigned now to P3. So P3 is running, P2 isn't ready, but the state of P3 is that that process was in the critical section was interrupted. So P3 is running, P3 is running, and applies a P operation. What is going to happen? Decrement the value of the semaphore by 1. And the P operation says, if the value is less than 0, block the process, send it to the semaphore queue. So P3 comes here. And the CPU is idle. And then the OS says, well, P1 gets a CPU now. So P1 is running, and P1 tries to get into the critical section, the same critical section. Apply the P operation, this is decremented. Is the value of the semaphore less than 0? Yes. So P1 comes here into the cell. Those two processes will not get into the critical section until P2 gets the CPU again, P2 continues running, and applies the V operation on lock. The V operation says, let's suppose P2 is running and get out of the critical section. And says, okay, the first thing is increment the semaphore by 1, and if the value is 0, less than 0, move the process to the ready queue. So this one, P2 is there. P3 comes here, right? And then P2, eventually, let's suppose that gets into back to ready. Now P3 gets in, P3 is running, P3 is running from here to there, P3 is running, and then apply the V operation, enter the critical section, get out of the critical section, apply the V operation, increment this by 1, so P1 gets here. I'm sorry, this is not ready. P1 goes back here, so P3 is running. When it's out of the critical section, if there is a timer interrupt, we can send P3 here. P1 gets the CPU. P1 goes in the critical enter the critical section. When the P1 applies the V operation, this value goes to 1. Okay? So you have to take 2 or 3 processes. The best way is in a board. Oh, I don't have the markers. Okay, let's see if we can do this.
Professor, I got one.
Well, it works. Let me see if that one works as well. I accept yours as well. Thank you. All right. And there's another one. Okay. Let's make the lights and the lights on. All right. I think this is going to be better. This is running. Can you see from the back? This is ready. This is wait IO. Wait on semaphore. All right. Dispatch. Timer. Can you see it on here?
Can you turn it, bro?
Can you see? Which one is this one?
Just one.
SIO? This one? V on semaphore. And this is P on S. Okay. S equal 1. And here we have P5, operating system has to apply a scheduling algorithm to select which one is going to get the CPU. And we say the highest priority is P4. So P4 is dispatched. So P4 is running, okay? So we have here P4, P5, and P3. All right. So P4 is running, and let's say that P4 applied the P operation, right? This is a critical section. P4 applied the P operation, and so the P operation says, decrements the value of the semaphore by 1. If the value of the semaphore is less than 0, block the process in the semaphore queue. But is less than 0? No. So the process continues running and enters the critical section. While in the critical section, if there is a timer interrupt, we know, remember, we cannot have interrupts where we are executing P or P, because remember that we disable interrupts, apply P, enable interrupts. So if I ask, can we have a timer interrupt in P? No. But in the critical section, this is a standard code. So if there is a timer interrupt here, what is going to happen? What does it happen to a process that is running and there is a timer interrupt? Back to ready, right? So P4 comes back here, and the CPU is idle. Each time the CPU is idle, the OS is going to apply the scheduling algorithm and it's going to dispatch another process. Let's suppose it dispatches P5. So P5 gets the CPU, and then it's running. And eventually, P5 wants to enter the critical section, and to do that, has to apply the P operation. Lock. Decrement the value of the semaphore by 1. Is the value of the semaphore less than 0? Yes. So P5 gets here. CPU is idle. So we dispatch P3, let's say. P3 is running. And let's suppose that P3 has a read operation here. That is an SIO, right? Transforming to SIO. So P3 comes. CPU is idle. Yes.
Does the suspend state play a part in this too? Like
This one,
suspend
right here.
up there, yeah, that play a part on
But we don't have anyone there because the process that was running, that was P3, initiate the IO operation, right? But we can have it later. Okay? So let's assume now that P4 is dispatched. Because the CPU was idle, right? P4. And it was here. So P4 is running. Get out of the critical section and apply a P operation. What does it happen? This one is incremented by 1. And the P operation asks if the value is increment the value by 1, and we ask if the value of S is less or equal to 0, then in this case is 0, we're going to remove this process from the semaphore queue and place it back into the ready state. Alright? And P4 is running. And then, well, P4 is running, but P4 is somewhere over here. Then if there is an I/O interrupt, what is going to happen? If there is an I/O interrupt, P4 will be suspended, so the OS needs a CPU to handle the interrupt. Are you following me so far? And then the OS, what it's going to do, it's going to move P3 right here, and then give back the CPU to P4, right? And P4 resumes execution, all right? Then, okay. So let's assume there is another timer interrupt here for P4. So P4 goes back to this place. And we dispatch P5. P5 was here when applied the P operation on both blocks, right? So it continues to enter the critical section. And then let's say that it applied the B operation. If it applies the B operation, this one goes to 1, the initial value, and P5, so we say, if the value is less than 0, we move a process, but there is 0, the value is less or equal to 0. But now the value is 1, so we don't have to remove any process because this is empty. And then P5 enters the critical section, can get out of the critical section with the B operation, and eventually go somewhere IO or any other operation. So this is the way probably to study this. To take 2 or 3 processes, and then take the diagram and say, well, this process execute B, this execute B, etc. Okay? And then now the critical section, at that moment, the critical section is free, is available for any process. Are you following me so far? Getting an idea of what is going on? So remember, when we apply the P operation, the semaphore is decremented, and if the value is less than 0, we block the process. If we apply the B operation, the value is incremented by 1. If the value is less or equal to 0, we move a process from the semaphore queue into the ready state. That's what we have done. Now I ask the question again. If a process is running and that process applies a P operation, does it block? A process is running. Let's say let me take P3. What is it? P3 is running, is here, and apply a P operation. Does it block? No. Okay? Now, if P4 is there, and P3 applies P operation, does it block?
Yes.
Yes. If there is another process within the critical section, any other process that tries to get in is blocked. So the answer would be, it depends. If there is another process in the critical section, or you can say if the semaphore is a negative value, but if there is, what it means that the semaphore is negative is that there is another process in the critical section. So if there is another process in the critical section, the process block, the running process block on the semaphore queue. Otherwise, it continues running and gets into the critical section. Is that clear? So you see, we can have two kind of questions, one related to semaphores, one related to the example we did the other day with 3 processes with a timer interrupt, I/O interrupt, and a system call. Remember? We're going to review that the day, Monday before the exam. Okay, so with P and B, we can do process synchronization. We enforce mutual exclusion, and we can easily avoid race condition, right? Okay, but that also comes with an additional, let's say, way of thinking when we're writing programs. Because now we have to learn to write programs that execute concurrently. Because we can synchronize processes without asking if the value of the array is n, then we can avoid many questions. And you will see soon that there are, in operating system, there are like five to seven algorithms that are used to explain how to use concurrency and how to write programs concurrently. Because it's different than to do sequential execution. The program that runs sequentially. So we need to, well, this is, what we're saying here is about the mask, all right? So this is what we explain about the mask. This is the P operation to describe what we do. But in the way we have to write this algorithm is not as we have it there explicitly with the data structure and so on. You say P on S is S get S minus 1 if S less than 0, blah. We know that it blocks in the same way. And for Bs, S equal S plus 1 if S is equal or less than 0, move process from SAM Q to ready. That's the way you have to learn, not with all the steps of the algorithm. Okay. So now let's say this. This is B, decremented by 1. If S is equal or less than 0, then the Q some process on the semaphore Q. Okay, this is the way we see P and B as lock and unlock. So when we're writing programs using semaphores, every time that we need to lock a critical section, we apply P. Every time that we unlock, we apply B. The value of S in our example is 1, but there are other cases where the value of S could be different than 1. Let's see how does it works at the machine level. So do you remember that we started with a small machine and we created an interrupt handler and so on. Okay, little by little we have created the loader, the interrupt handler, the dispatcher, runtime library, etc. So let's suppose that we have those pointers ready and running. And there is a semaphore. Initial value is 1, pointer, no. P1 is running, P2 is in ready. So this is what is going on inside the computer. And P1 is trying to enter the critical section. To do that, P1 has to apply a P operation, right? So it applies, semaphore, I said decremented by 1. The value of the semaphore is 0, and we know that if the value of the semaphore is less than 0, the process is blocked, otherwise it continues running, right? So P1 enters the critical section and is running. While running in the critical section, there is a timer interrupt. So, well, P1 goes back to ready and P2 goes into the running state. Now, running, P2 is running. P2 is running means that we copy the context of the PCB into the CPU, right? So P2 is running, that's context switching what we did. There is a timer interrupt while P1 is in the critical section, right? And P2 goes to CPU. So if P2 applies a P operation and tries to enter the critical section, we decrement the value of the semaphore by 1, and then P2 will be sent to wait on semaphore. And this is the state. P2 is blocked on a semaphore. Then, as the CPU is idle, then we dispatch P1, and P1 gets the CPU. So now P1 continues running, P2 is blocked on semaphore Q. If P1 apply a B operation to get out of the critical section, to unlock the critical section, then the semaphore is incremented by 1, and P2 is sent to the ready state. Exactly what we were doing with the state diagram, but this is inside the computer. All right. Example of an algorithm called the bounded buffer producer consumer. This is an algorithm that we're going to use to explain how to write programs concurrently using P and B or similar synchronization primitives. The bounded buffer producer consumer is a program that has two processes, producer and consumer. And there is a buffer of a certain size, and the producer is going to produce items and insert them into the buffer, and the consumer is going to get items from the buffer and consume them. Consume could be print out something. Produce could be do a calculation and place the value there. For instance, we can have a program that is computing the interest of all the accounts in a bank and place the values here, and the other one is taking them and print them out. That's an example of producer-consumer. So this is very common in operating systems. Examples of a producer-consumer solution. In a multimedia system, P1 is reading data from a network connection and stores it in a buffer, temporary memory area. And P2 is reading the data from the buffer and feeding it into the video or an audio hardware. That's another example. Okay, so we have two processes, one that is producing some values and placing them into a memory location that we call a buffer, and the other one that is taking those values and consuming them, doing something with those values. But there is something there. These are two processes that are in the ready state.